So, we are looking into the solution of non-homogeneous partial differential equations, which will be typically occurring in a system where you are working with a multidimensional problem or transient problem in several dimension in space, and where you are having a volumetric source or sink term like continuous heat generation within a volume of a reactor or something like that. Now, the typical analytical solution that you can obtain by using Green's function that we have looked into, by imposing one unit impulse into a system, you will like to simulate the effect of overall non-homogeneity in your governing solution. Now, we have seen how to formulate the Green's function. We have already seen what are the typical steps those are involved in getting the solution. It is a lengthy one. The first step is given a particular problem, you have to construct and formulate and solve for causal Green's function. Then you have to obtain the adjoint Green's function. Then you have to connect adjoint Green's function with the original problem. Now, if it is a self adjoint operator, we know how to find out whether the operator is self adjoint or not. If it is a self adjoint operator, then you need not go to the third step, that is evaluation of adjoint operator, adjoint Green's function, because in that case both Green's function and the adjoint Green's function are identical. Okay. And we have looked into an example for ordinary differential equation where we have applied the Green's function method in order to obtain the solution. Today, we will extend the same analysis for the solution of partial differential equation in a multidimensional problem. You consider the equation that you are going to solve is, let us say, delta square u is equal to f. F may be a typically a non-homogeneous function of x, y, z, and the operator delta square, let us say it is a Laplacian operator, del square del x square plus del square del y square plus del square del z square. Okay. Now, we have to first construct the causal Green's function. The causal Green's function will be nothing, it will be grad square g x y z slash x naught y naught z naught is equal to delta x minus x naught delta y minus y naught delta z minus z naught. Okay. Suppose this original problem u is having a boundary condition. Let's say it has two boundaries. One is SR and another is SD, and the boundary condition is n hat grad of g plus Cg is equal to 0 on, let us say, SR and Cu. Okay. Let us say it is something. Let us say it may be non-homogeneous H, and on SD, let us say u is equal to something. This boundary condition is a mixed boundary condition. This is unit normal. Okay. So, this is basically grad of u means plus Cu is equal to H on some surface. Let us dividing the boundary surface into two parts. One is SR, another is SD, and on SD, let us say u is having a Dirichlet boundary condition, on SR it is having a mixed boundary condition. Okay. So, the corresponding causal Green's function will be in this form, right, and the corresponding boundary conditions will be at grad of g plus Cg is equal to 0 on SR and g is equal to 0 on SD, right. So, whenever we are formulating Green's function, we are forcing the boundary conditions to be homogeneous. SR and SD, the boundaries, let us say we are dividing the boundary into two parts, one is SR and another is SD, surface. Okay. So, on this surface, let us say mixed boundary condition is prevailing, and on the other surface, let us say Dirichlet sort of boundary condition is prevailing. So, whenever you are formulating the causal Green's function, you are forcing these non-homogeneous even on the surfaces or boundaries to be homogeneous. Okay. Now, our aim is to find out what is the expression of this Green's function. Once we know the expression of Green's function, then 90% of our job is over. Okay. Now, there are two methods to obtain the Green's function in general. The methods are First is full eigenfunction expansion. Second one is partial eigenfunction expansion. Okay. In full eigenfunction expansion, you consider given a Green's function, you consider the corresponding eigenvalue problem in all the directions in x, y, z. So it's basically a 3-dimensional problem or 2-dimensional problem depending on the original operator, whether the operator is 2-dimensional or 3-dimensional. In partial eigenfunction expansion, you consider the eigenfunction in a particular direction. Suppose it is a 2-dimensional problem in x and y, and you consider the corresponding eigenvalue problem in, let's say, in the x direction, okay, and express your Green's function as a summation of all these eigenfunctions. That is partial eigenfunction expansion. In full eigenfunction expansion, you consider the corresponding eigenvalue problem in all directions and express your Green's function with the multidimensional eigenfunctions. Okay. Now, for a bounded domain, that means for if your domain is bounded, let us say in this problem it is a Laplacian operator, let us say del square del x square plus del square del y square. X is bounded between 0 to 1, y is bounded between 0 to 1. For a bounded domain, generally full eigenfunction expansion is used. When one of the domains is unbounded, for the sake, let us consider a parabolic partial differential equation like del del t minus del square del x square. In this case, x is bounded from 0 to 1 and t is unbounded starting from 0 to onwards, let us say infinity. Okay, so t dimension is basically unbounded. So you consider you have to consider partial eigenfunction expansion in order to obtain the Green's function. So since this problem is a bounded problem and where the operator is Laplacian operator and it is a bounded domain, we will be using full eigenfunction expansion. Bounded domain. Okay. Now, our Green's function is del square g is equal to delta x minus x naught, delta y minus y naught, delta z minus z naught with the boundary condition grad of g plus Cg is equal to 0 on the surface SR and g is equal to 0 on the surface SD. Okay. So corresponding eigenvalue problem is can be written as del square phi, where phi is the eigenfunction, del square phi plus lambda phi is equal to 0. Right? If you remember, the form of the standard eigenvalue problem will be del square phi plus lambda phi. We have solved this type of problems whenever we have used we have considered the problems using separation of variables. Okay. So corresponding eigenvalue problem will be this, subject to homogeneous boundary conditions. Whenever you are having a standard eigenvalue problem, you remember you must be considering homogeneous boundary conditions. Okay. So corresponding boundary conditions on phi are grad of phi plus C phi is equal to 0 on the surface SR and phi is equal to 0 on the surface SD. Okay. Let us say there will be n number of eigenvalues possible for this case and corresponding eigenfunctions, let us say I, this is ith eigenfunction corresponding to ith eigenvalue lambda I. Okay. So this is the corresponding eigenvalue problem. Now so basically you can solve this equation. You have solved the eigenvalue problem number of times whenever we are considering separation of variables. Okay. So you know how to get the solution of this problem. Now Green's function is expressed in terms of the summation of these eigenfunctions. Okay. let us say by solving this standard eigenvalue problem, the solution you will be getting as phi I x y z. Okay. So, Green's function is expressed in terms of these eigenfunctions with a corresponding constant a I. Okay. So, this I runs from y to infinity. So, I is basically ith eigenvalue and phi I is the lambda is basically ith eigenvalue and phi I is the corresponding eigenfunction. So, you can write down. So, basically by solving the eigenvalue problem, you know phi I, the expression of phi I, okay, but the constant is unknown. This constant can be obtained by this relationship integration volume integral g and phi I dv phi I dv over v. You can write this equation the expression of constant a I provided. What is the condition of this equation? All the eigenfunctions are orthogonal. If all the eigenfunctions are orthogonal, you can multiply it both sides by phi j and integrate and open up this summation, right. If phi I and phi j are orthogonal to each other, then all the terms will vanish except one term, that will be phi I and phi I. Okay. So, this can be written if phi I or eigenfunctions are orthogonal to each other. Okay. In fact, the eigenfunctions for such systems are really orthogonal to each other. Okay. That can be proved. The proof goes like this: phi I, basically phi I's form an orthogonal set of functions. Let us say we have two distinct eigenvalues lambda I and lambda j. Okay. Corresponding eigenfunctions are phi I and phi j. So, governing equation of phi I is nothing but grad square phi I plus lambda I phi I is equal to 0, grad square phi j plus lambda j phi j is equal to 0, right. These two are the governing equations for phi I and phi j. Okay. Let us say this is equation number 1, this is equation number 2. You multiply equation number 1 by phi j and integrate. You multiply equation number 1 by phi j dv and integrate over the volume. You multiply equation number 2 by phi I dv and integrate over the volume and then subtract. Okay. If you do that, let us see what you get. Phi j grad square phi I minus phi I is over the volume, because this equation is valid over the full volume of the control system. Okay. Grad square phi j dv plus lambda I phi j dv minus lambda j phi j dv is equal to 0, right. Okay. So, in a compact form, you can write this integral as phi j grad square phi I minus phi I grad square phi j dv is equal to lambda j minus lambda I integral phi I phi j dv, right. Agreed? Fine. So, let us say this is right hand side and let us simplify the full left hand side and see what we get. For simplifying the left hand side, we use the identity grad of u of grad v. This is an identity that we are going to use to simplify those equations. U of grad of u v is nothing but u grad square v plus grad of u grad of v. Using this identity, we can simplify the full left hand side of the previous equation. Let us look into the left hand side. It is v phi j grad square phi I, phi j grad square phi I. Okay. So, what you will be getting is phi j grad square phi I, that means phi j grad of phi I minus grad of phi j grad of phi I. That will be the first term, that will be basically this term, okay, minus phi I grad square phi j, phi I grad square phi j. So, grad of phi I grad of phi j minus grad of phi I phi j grad of phi j, bracket close, let us say put a second bracket here, dv. Okay. So, what you get? You get v grad of phi j grad of phi I dv minus grad of phi I grad of phi j dv over the volume minus volume integral grad of phi j grad of phi I dv minus minus plus integral grad of phi I grad of phi j dv. Okay. So, last two term will be cancelling out, right. This last two term will be cancelling out. Now, these two terms can be again simplified by using Green's theorem, where you are converting a volume integral into a surface integral. Okay. By converting volume integral to surface integral, what you can do, this integral will be replaced by a surface integral and this grad will be gone. So, it will be phi j grad of phi I ds. You remember those 10 plus 2 mathematics, conversion of volume integral into surface integral, conversion of surface integral by into a line integral. Okay. We are using the Green's theorem, which is converting the volume integral into the surface integral. Okay. Minus s phi I grad phi j ds. Okay. Now, these two surfaces, because we are these two surfaces are basically boundaries of our problem, and this boundary is divided into two parts in the original problem, SR and SD, right. So, this integral will be again broken into two parts, one is over SR, another will be over SD. So, we continue evaluate left hand side. So, this will be over SR phi j grad of phi I ds plus over SD phi j grad of phi I ds minus over, this is the second term, SR phi I grad of phi j ds minus over SD phi I grad of phi j ds. Okay. Now, what are the boundary conditions are on phi I and phi j? The boundary conditions of phi I are grad of phi I plus C phi I is equal to 0 on SR, phi I equal to 0 on SD. What are the conditions on phi j? Same, because phi I and phi j are the same eigenfunctions which will be satisfying this equation only. So, grad of phi j plus C phi j is equal to 0 on SR and phi j is equal to 0 on SD. Okay. So, phi I equal to 0 on SD and phi j is equal to 0 on SD. So, this term will be off, this term will be off, because this is equal to 0 on the surface SD, phi I is equal to 0 on the surface SD. So, this term is 0, this term is 0, and grad of phi I is equal to minus C phi I. So, C is a constant. So, it will be on SR phi j phi I ds minus minus plus C on SR phi I phi j ds. These two terms are identically equal. So, they will be cancelling out. So, you will be getting 0. So, whole lot of left hand side will turning out to be 0, and your basically what you will be getting on the right hand side is lambda j minus lambda I integral phi I phi j dv is equal to 0, right. Since lambda I and lambda j are two distinct eigenvalues, they are not equal to 0, they are not equal. Okay. that means this integral will vanish. That means integral phi I phi j dv is equal to 0. That means phi I will form an orthogonal sets. So, all the eigenfunctions phi I forms an orthogonal set. So, the eigenfunctions are orthogonal to each other, therefore, we can write down this expression for the corresponding Green's function A I in this form. Okay. So, basically given a problem, you have to formulate the corresponding standard eigenvalue problem, and once you formulate the standard eigenvalue problem, you can get eigenfunctions. Once you get eigenfunctions, you can express your Green's function as the summation of all these eigenfunctions, and since eigenfunctions are orthogonal to each other, you have just seen the proof, and you can express all these the associated constant A I in this form. So, what is left behind? Since you have already determined eigenfunctions, the denominator is known to you, right? This denominator will be known to you because it is the integration of phi I, and phi I is known to you, and the numerator is still to be determined, because you do not know the expression of g, you do not know the explicit expression of g. If you would have known the explicit expression of g, that could have inserted here, and you know phi I could have evaluated this integral. But right now you do not know the explicit expression of Green's function. So, this has to be determined, the numerator has to be determined, then you can find out the coefficient A I. Once you find out the coefficient A I independently, then you can find an expression of Green's function explicitly. Okay. Now, we would like to find out the evaluation of numerator of expression of A I. Okay. So, for that you just consider the governing equation of Green's function x naught y naught z naught x y z slash x naught y naught z naught is equal to delta x minus x naught delta y minus y naught delta z minus z naught. Okay. And the corresponding eigenvalue problem is grad square phi I plus lambda I phi I is equal to 0. In order to get the numerator of the expression of A I, what you do? You connect this equation g and phi I. How to connect that? You multiply the equation number 1, let us say this is equation number 1, this is equation number 2, you multiply equation number 1 by phi I dv. Okay. You multiply equation number 2 by g dv and integrate and subtract. That is how you connect the two equations. Okay. So, it will be simply integration of del grad square g phi I dv minus grad square phi I g dv. This integral is over the volume because both the equations are valid over the control volume, plus lambda is a constant. This will be integration phi I g dv is equal to, what is this? This will be phi I x y z, which will be a function of x y z as well, delta x minus x naught delta y minus y naught delta z minus z naught dv over volume. What is this dv? dv is nothing but dx dy dz, and this volume integral is nothing but over x. This will be basically a triple integral, one will be over x, another will be 1 over y, third one will be the over z. So, what will be the right hand side? Right hand side is nothing but phi x naught y naught z naught. Okay. Now, since the boundary conditions on g are homogeneous, since the boundary condition on phi are homogeneous, exactly like the previous one, you can evaluate these two terms and they will turn out to be 0. We have really did that experience, these calculations. Okay. So, these two terms will be vanishing. Okay. Again, you use the same identity, grad of u of grad v is equal to u grad square v plus grad of u plus grad of v, right. Using that, we have done this thing just a few minutes back. So, simplification of first two terms will lead you to 0. So, what is left behind is lambda I phi I integral of phi I g dv is nothing but phi I x naught y naught z naught. So, integral of phi I g dv is nothing but phi I x naught y naught z naught divided by lambda I. What is this? This is nothing but the numerator of a governing equation of A I. If you look into the expression of A I, the numerator is integral of g phi I dv. Okay. Whatever we have got is nothing but same integral of g phi I dv, where it in terms of the eigenfunctions and eigenvalues. So, what will be the final form of expression of A I? A I is phi I x naught y naught z naught divided by lambda I phi I dv. Okay. And what is Green's function? Green's function will be represented as A I summation of A I phi I x y z. So, what you have to do? You have to construct the corresponding eigenvalue problem. You have to solve the eigenfunctions that we have done number of times whenever we are looking into the problems using separation of variables. Once you get the eigenfunction, then you can write down your A I. So, you can express your Green's function in term as a summation of all these eigenfunctions. Okay. And the corresponding constants will be evaluated by using the orthogonal property of these eigenfunctions, and the numerator and denominator can be separately evaluated, and it would be turning out to be a function of eigenfunction and eigenvalue only. This is the eigenfunction, a known one, this is the corresponding eigenvalue, and this is basically an integral which can be evaluated once you know the eigenfunction. Okay. If you remember the eigenfunctions that you have used or calculated whenever you were solving the problems using separation of variables, there was a constant appearing in front of it. Okay. So, you can further simplify it by forcing the eigenfunctions to be orthonormal. Okay. Orthonormal means their norm is equal to 1. Norm means integral of phi I to norm of a function f is basically defined as integral of f times dv, that is called norm. Orthonormal means its norm is 1, its length, its norm is nothing but representing length for a vector. For a continuous function, the norm basically phi I times phi I dv is equal to 1. So, this is called orthonormalization of a function. Or in other words, if your function is orthonormal, that must satisfy this property. Okay. So, if your eigenfunctions are orthonormal, or if you force the eigenfunctions to be orthonormal, in the process, basically suppose the eigenfunction will be turning out to be c sin n pi x. Let us say in a one dimensional problem, if you force phi I these eigenfunction to be orthonormal, it will be nothing but c square phi I into phi I c square. Let us say x domain of x is from 0 to 1 sin square n pi x dx is equal to 1 for one dimensional problem. Okay. So, what is this? This will be nothing but half. So, c will be under root 2. So, phi I is equal to root 2 sin n pi x is basically an orthonormal function. So, you can always force your eigenfunctions to be orthonormal by setting this integral to be 1. Therefore, if your eigenfunctions are orthogonal as well as orthonormal, then this integral in the denominator will be turning out to be 1. In that case, the expression of A I will be further simplified to x naught y naught z naught divided by lambda I. Okay. So, basically you have to consider a standard eigenvalue problem. You have to find out the eigenvalue and the corresponding eigenfunctions. Once you know the eigenvalues and eigenfunctions, then you can express G as a summation of all these eigenfunctions, and the corresponding constant can be evaluated from the eigenvalues and the eigenfunctions only. and you can determine G, your Green's function, completely. Okay. Now, we will be looking into an example that will clarify the subsequent calculations. Let us say we are trying to solve a problem something like this: del square u del x square plus del square u del y square is equal to let us say f of x and y. Okay. Then you must be maybe having non-homogeneous, homogeneous boundary conditions on x and y. Okay. So, we would like to construct the causal Green's function for this operator delta square. Okay. What is delta square? Delta square is nothing but del square del x square plus del square del y square. So, we formulate the causal Green's function as the first step for the solution scheme. That will be nothing but del square G del x square plus del square G del y square is equal to delta x minus x naught delta y minus y naught. Okay. Now, what is the corresponding equivalent eigenvalue problem? The corresponding equal eigenvalue problem will be del square phi del x square plus del square phi del y square is equal to plus lambda phi is equal to 0. Okay. That is grad square phi plus lambda phi equal to 0. The grad square is del square del x square plus del square del y square. Okay. And let us say in this problem we have 4 boundaries, that means 4 surface. One surface is located at x equal to 0. Okay. Another surface is located at x equal to 1, another surface is located at y equal to 0, another surface is located at y equal to 1. Let us say all these surfaces x equal to 0 and 1, y equal to 0 and 1, they are having some, let us say, some non-homogeneous boundary condition of the original problem. So, whenever you are constructing the Green's function, causal Green's function, you are forcing all these non-homogeneous to be homogeneous. That means all the boundaries, let us say Dirichlet boundary conditions are prevailing. So, value of G is equal to 0 or on this surface, on these 4 surfaces. Okay. Similarly, phi, whenever you are solving the corresponding eigenvalue problem, all the boundary conditions on phi, all the 4 surfaces will be equal to 0, because the standard eigenvalue problem means all the boundary conditions have to be homogeneous. Phi on all 4 boundaries located at x equal to 0 and x equal to 1, y equal to 0 and y equal to 1. Are homogeneous. Okay, that means phi is equal to 0 at x equal to 0 on the surface at x equal to 1, surface at y equal to 0, surface at y is equal to 1. Okay. Now, you know how to solve this problem, how to find out phi. How to find out phi? This is standard eigenvalue problem. You consider phi is a product of function of x alone and function of y alone. Right, phi is a product of function of x and function of y. Let us say phi is equal to x times y, where x is a function of x alone, x of x and y of y, and substitute in a governing equation. What you get is x double prime by x. X double prime is nothing but d square x dx square plus y double prime by y. This should be is equal to minus lambda. That is your governing equation. Okay. And x double prime by x is equal to minus lambda minus y double prime by y. This is a function of x alone, this is a function of y alone, they are equal, that means they are constant. This constant can be positive, negative or 0. If the constant become positive or 0, you will be getting a trivial solution. So, this constant must be negative. You know, we have gone through all these logics previously, okay, minus alpha square. So, d2x dx square plus alpha square x is equal to 0. Now, x varying part must be satisfying the boundary conditions on x of the original problem. What is that? At x equal to 0 and x equal to 1, your capital X is equal to 0. Okay? And we have solved this problem number of times, right? The corresponding eigenvalues are n pi and corresponding eigenfunctions are sin n pi x. So, alpha n is equal to n pi and x n is, let us say, some constant a n sin n pi x. Okay. Similarly, we can solve the y varying part from this. Y double prime by y will be nothing but minus lambda plus alpha square. Okay. Again, it is a constant. So, and this constant has to be a negative constant, otherwise you will be getting a trivial solution. So, let us say this is minus beta square. So, d2y dy square plus beta square y is equal to 0 is the governing equation for y, with the condition at y is equal to 0 and y equal to 1, your capital Y is equal to 0. Okay. And the corresponding eigenvalues are beta m are m pi, where m runs from 1 to infinity, and corresponding eigenfunctions are, let us say, b m sin m pi y. Okay. So, what is your phi mn? Phi mn, phi is nothing but capital X x n multiplied by the y m. So, a n multiplied by b m, two constants. So, let us say it will be a new constant, let us say c m n sin n pi x sin m pi y. Okay. So, what is the corresponding Green's function? So, you have evaluated the eigenfunction, the corresponding eigenfunction. Okay. Now, you can express Green's function in terms as a summation of all these eigenfunctions. Okay. It is nothing but summation over m, summation over n, phi m n x naught y naught, phi m n x y divided by lambda m n phi m n square dx dy, this is over x, this is over y. Okay. So, that is the expression of the Green's function. If you look into just look in your previous notes. So, it is that what is lambda m n? Lambda m n can be obtained from here. Lambda m n is nothing but alpha n square plus beta m square, right. From this, what is alpha n? It is n square plus m square pi square, right. Is this clear to everyone? Okay. Now, what you do? So, phi m n you have already determined. Phi m n x naught y naught, you will be simply substituting x by x naught and y by y naught. Lambda m n is known to you because m and n are the running indices and pi is a known constant. Only thing is the evaluation of this constant c m n, that can be obtained by forcing the eigenfunctions phi m n to be orthonormal. Okay. You make phi m n to be orthonormal, that means you make this value to be 1, then it will be further simplified, and in the process you will be evaluating the constant c m n. So, it will be serving you a dual role. Okay. Making eigenfunctions to be orthonormal, that means phi m n square dv is equal to 1. It is a two dimensional problem. So, dv will be replaced by dx dy. So, integral and x running from 0 to 1, y running from 0 to 1, phi m n is c m n square sin square n pi x sine square m pi y dx dy is equal to 1. Okay. So, Cmn square integral sine square n pi x dx, that will be half, integral sine square m pi y dy over 0 to 1, it will be again half. So, it will be 1 by 4. So, it will be equal to 4. So, Cmn will be nothing but 2, right. So, what are your eigenfunctions? Your eigenfunctions are now completely defined. 2 sin n pi x sin m pi y, and now your Green's function is completely defined. G x y x naught y naught is nothing but is minus the m n phi m n x naught y naught phi m n x y. So, 2 into 2 4 sin n pi x sin m pi y sin n pi x naught sin m pi y naught divided by lambda m n. Lambda m n is nothing but pi square into m square plus n square, and the this integral on the denominator will become 1 because we have forced the eigenfunctions to be orthonormal. So, that will be your final expression of Green's function for this problem. Okay. Right. So, still the work is left because it is halfway, because we have not solved the real problem. Actual problem is the solution of u. Okay. Now, in the last class and the previous class, we have seen how to find out the adjoint operator, and we have found out the operator like d square dx square is a self adjoint operator. Similarly, it can be found out, it can be obtained, you can do it by yourself also, that this Laplacian operator del square del x square plus del square del y square plus del square del z square is a self adjoint operator. This operator del square del x square plus del square del y square is also a self adjoint operator. So, in this problem also we need not go for the finding out to for adjoint Green's function. So, you can start with the we can carry out your further analysis with this expression of Green's function and connect Green's function g with u. Let us look into a complete example. Let us solve the equation del square u del x square plus del square u del y square. The u may be temperature is equal to a known function of x y. It may be, this non-homogeneity can be function of x alone, it may be function of y alone, it may be function of x and y both, it may be a constant. If it is a constant or if it is not a constant, that functional form is explicitly known. Now, we have 4 boundaries located at x equal to 0 and x equal to 1, y equal to 0 and y equal to 1. Let us say u is equal to 0 at x equal to 0. Okay. U is equal to some function h at x equal to 1, u is equal to 0 at y equal to 0, u is equal to k of x at y equal to 1. That means, there are 2 non-homogeneities on the boundaries and 2 homogeneities, two boundary conditions homogeneous and 2 boundary conditions are non-homogeneous, and our aim is to find out u as a function of x and y. Okay. So, we construct the corresponding causal Green's function the same way we have done previously, and we will be using that expression of Green's function as it is, because we have already solved the problem. So, causal Green's function will be del square g del x square plus del square g del y square is equal to delta x minus x naught delta y minus y naught. Okay. And g is homogeneous at all the 4 boundaries, at x equal to 0, at x equal to 1, at y equal to 0, at y equal to 1. And we have already solved this problem for g by using full eigenfunction expansion. What is the expression? G x comma y, x naught, y naught is nothing but summation of over m summation over n 4 sin n pi x sin m pi y sin n pi x naught sin m pi y naught divided by m square plus n square pi square, that we have already found out. Okay. Now, since this operator del square del x square plus del square del y square is a self adjoint operator, you need not to solve for the adjoint Green's function. So, you have to connect g and u right away. How to connect that? Simple. You have the governing equation of u del square u del x square plus del square u del y square is equal to f x y. You multiply both sides by g dx dy. You multiply both sides of the governing equation of g by u dx dy and integrate and subtract. That way both the equations are connected. If you do so, whatever you will be getting is g del square u del x square dx dy plus g del square u del y square dx dy minus u del square g del x square dx dy minus u del square g del y square dx dy is equal to integral f of x y times g dx dy minus u x y delta x minus x naught delta y minus y naught dx dy. One integration over x, another integration over y. So, let us look into the right hand side. The right hand side will be nothing but f x y g dx dy minus u of x naught and y naught, right. This will be simply u of x naught and y naught. Now, f is a known function, let us say x, and g is a known function summation of something, and you can generally you can of course integrate this thing analytically. It will be integration of x sin n pi x dx 0 to 1, integration of sin m pi y from 0 to 1. So, this integral can be analytically evaluated. Agreed? F x y is a known function, or it may be constant, whatever. If it is in an amenable form, you can evaluate this integral analytically by hand. If it is a complicated one, you can evaluate this integral by any numerical subroutine using a trapezoidal rule or something, Simpson's rule. Okay. So, this is integrable in analytical form. U x naught y naught that you are going to find out. So, let us evaluate the whole lot of left hand side. Okay. On the left hand side, you are having the term g del square u del x square dx dy. Okay. And let us say this integration is over x, this integration over y. G del square u del y square, or change the order of integration, g del square u del y square dy dx. This integration over y, this integration over x. U del square g del x square dx, this is over x, this is over y. U del square g del y square dy dx, this is over y, this is over x. Evaluate the first integral by parts. Okay. So, what do you get? If you evaluate the first integration by parts, you will be getting first function integral of second function g del u del x from x equal to 0 to 1 minus integration over x del g del x del u del x dx dy. Agreed? The first integral I am doing by parts and the second integral remaining as it is. So, likewise the 4 integrals. So, next one will be x g del u del y from y equal to 0 to 1 minus del g del y del u del y dy dx, right. The next one will be y u del g del x over x equal to 0 to 1 minus this over x del g del x del u del x dx. The outer integral remains the same. The fourth one is x u del g del y from y equal to 0 to 1 minus y del g del y del u del y dy. The outer integral remains the same. Now you simplify. So, this equation, this term will be nothing but double integral over x and y del g del x del u del x dx dy. Agreed? This term will be nothing but double integral over x and y del g del y del u del y dx dy. This term will be double integral del g del x del u del x dx dy, and this will be double integral del g del y del u del y dy dx. Now, this one and this one are identical and opposite in sign, because there is a minus sign out here, minus minus plus. So, it will be cancelling out. This one and this one is minus. They are these quantities are identical. This is minus minus plus. So, they will be cancelling out, right. Now, evaluate all the surfaces y g at 1. What is g at 1? 0. So, that is gone. G at 0, that is gone, that is 0. So, this is off, the whole term is gone. So, this equation, this full term is not there. Okay. G at 1, that is 0. So, this term is also off. G at 0 is 0, this term is also off. Minus u at 1. What is u at 1? Hy. It is a known function, it may be constant. Hy del g del x evaluated at y equal to 1. You know the expression of g as a function, explicit function of x and y. You can take derivative del g del x. You can evaluate that del g del x at y equal to 1. So, this is also known to you. So, this is over y. Here, no, okay. Now, u at 0, that is 0. So, the second term of the limit will be gone, okay. Minus over x u at 1. What is u at 1? Kx, right, kx. Similarly, you can find out del g del y at y is equal to 1, okay, at x equal to 1. This is over dx over x. So, you know expression of g, you can find out del g del y, you can evaluate that at x equal to 1. Hy is a known function, kx is a known function, or they may be constant. So, again these two integrals can be evaluated analytically. So, let us summarize what we get ultimately. Ultimately, you will be getting 1 integration over y h del g del x at y equal to 1 dy minus kx del g del y at x equal to 1 dx is equal to double integral f g dx dy minus u x naught y naught. Okay. So, what is the expression of u x naught y naught? It will be simply, it will be coming out on this side. So, double integral f g dx dy minus 0 to 1 h minus minus plus del g del x at y equal to 1 dy plus 0 to 1 k del g del y at x equal to 1 dx, right. Now, f is having, g is having is a function of x y as well as x naught y naught. You are integrating over x and y. definite integral. So, those will be gone. So, it will be function of x naught and y naught only. Okay. Whatever the result you will be getting, that will be in the form of x naught, function of x naught and y naught only. H is a function of y alone, and del g del x, y is gone. So, it will be function of x naught. Okay. Similarly, so since you are doing away with y, you are integrating over y, again it will be function of x naught and y naught. Similarly, you are doing away with x, and it will be function of x naught and y naught, and then you will be getting a final expression of u as a function of x naught and y naught, and change the variables, dummy variables x naught and y naught to running coordinates x and y. You will be getting the solution of u as a function of x and y. You see the important points. There are 3 sources of non-homogeneities in your equation and boundary condition. There are two non-homogeneities in your boundaries and 1 non-homogeneity in the governing equation. So, there are 3 integrals are appearing here. 1 non-homogeneity is in a governing equation. The governing equation is valid for the whole volume of the system. So, these will correspond to the non-homogeneity appearing in the governing equation, because a double integral or dv is appearing. These 2 non-homogeneities are appearing because of the non-homogeneities appearing on the boundary conditions. On the boundaries, that is why you are getting one integration in one dimension only. Okay. If all the 4 boundaries are non-homogeneous of your original problem, you would have landed with 4 one-dimensional integration and 1 two-dimensional integration. Okay. So, we have considered dirichlet boundary conditions. Any kind of boundary conditions, for example Neumann or mixed, can be taken care of. Okay. Thank you. And the typical example we have looked into, there are 2 types of problems that one can encounter. One is transient problems. Okay. Transient problems means it will be involving one dimension in time, 1 or more dimensions in space, or steady state problem, steady state multidimensional problems. That means the independent variable temperature or concentration may be function of x and y both, but it will be independent of time. So, in that case also you will be getting the a partial differential equation, and the corresponding operator is a Laplacian operator when it is a steady state problem. Now, more often the steady state problem may not be important, the transient problem is important. Okay. Like the example I was giving, you are having a nuclear fuel element, and which temperature is a function of r and t, and z dimension is so long that all the variations of temperature in the z direction is negligibly small. So, in this case the governing equation will be a function of r and time. Okay. So, it is a function of time and a function of space. Now, so this kind of parabolic non-homogeneous transport equations are important in many cases